Hi, I'm going to be talking about the sorting problem from Chapter 7 of your book, and we're going to talk about the selection sorting algorithm. So basically we understand with sorting, our goal is we're given some list as input, and our goal is to produce a sorted list by running it through some sorting algorithm. And our goal is at the other end of this sorting algorithm, it should have the property that for any I, list I should be greater than or equal to list at index I minus 1. Right? So, and this of course would be true for I equals 1 to the length of the list, which I'm just going to call n here, and I'm going to write n minus 1 because we can't actually access the last index of the list. Normally we iterate starting at 0, but since we're accessing I minus 1, that would be 0 when I equals 1. So as an example, let's consider the numbers 1 through 5. So if this is list, I'll do list prime to indicate that it's the sorted list. And so that would be some array of 5 elements, and let's just use 1, 2, 3, 4, and 5. So those are just the decimal numbers, and I'll draw them as an array. And this would be at index 0, at index 1, 2, 3, and at index 4. And so n would equal 5, the length of the list. So this would be a sorted list because it satisfies this property. The list at index 1 is greater than or equal to the list at index 1 minus 1, which would be 0. All right, so that's kind of our condition. All right, so that is the condition. It's important that it can be checked. That's part of algorithms. So an example of input to a sorting algorithm would be also a list, but possibly in some different order. So I'm going to just do my best to kind of randomly permute that. So let's do 3, 1, 2, 5, 4. And by the way, if you didn't know this, people are very bad at coming up with random sets. We almost try to find anti-patterns which are predictable. If you're ever playing rock, paper, scissors or something, you can use that to your advantage. So, but this is my attempt at a random permutation. Permutation, as you probably know, just means shuffling in a different order of the list. So this would be something like the input. Of course, the input could have already been sorted or sorted in reverse. There's all different kinds of special cases you'd have in a test plan. And our problem here is to come up with this algorithm that takes you from here to here. And the first algorithm that we're going to look at, we're going to go through the algorithm design process a little bit. We're not going to go through Polya's whole process for this, just because that would be overkill and there's not time for it. But we kind of already have a well-boiled problem here, right? I've established some notation, n for the length of the list. I've got this diagrammatic notation for the arrays. I've given the list a name. So we've done some of these kind of steps. But now let's begin to develop an algorithm. So let me take a sip of my coffee. Yum. And there are a few algorithms we're going to talk about. The first one is, and maybe you want to pause the video and think about how you do this. Don't Google it, but just think about how you would sort a list of numbers. So you might have maybe some post-it notes would be a good example here, right? 1, 2, 3. That's a trivially small set of numbers. So let's write A, B, C. Let's do letters instead of numbers, right? So if I were to just shuffle these around in some random way, how would you go about sorting them? Well, one idea is just to scan through and look for the smallest thing. A should go first, right? So I can put it down here first. And then now what's the next smallest thing that's left? B. Okay, that should go second. And once I've done two of them, there's only one place the last thing can go. I don't even need to search anymore. So this would be an example of selection sort. The way that it works is you scan. Let me kind of show you that again. You scan through for the smallest item, and when you find it, you grab it, and you put it at the beginning of a sorted list. Now, it's important that initially this entire list is just random. So if I shuffle it again, it's still random. It doesn't matter, right? But what I'm building down here at the bottom always stayed sorted. Right? So that kind of invariant is important to remember about an algorithm when you're designing it, because it helps you know that the algorithm is correct, because I can guarantee that everything here is always sorted. And if I can always prove that as the current index kind of proceeds through this list, then I know the algorithm is correct. One thing, though, is I don't need to put that list down there. I can just imagine that there's some pointer to the sorted half of this array. So right now, nothing's been sorted. If I find the smallest thing, I can actually swap it with the first item in the list, because, you know, unsorted and unsorted, it doesn't matter which order it goes, it's still unsorted. But then I put the smallest thing at the beginning of the list, and now I can increment this sort of index, and everything to the left of the pen I know is sorted. So instead of making a completely different pile, or making a completely different array, it's possible to sort the array in place, to reuse the memory locations that held the original data in order to hold the sorted data. And that's called an in place. I'm just going to write that down. In place. Algorithm. You don't need to allocate new data. There are algorithms, there are sorting algorithms that can't be done in place, like merge sort, which I don't know that we'll cover in this course. Right? But that's an important property, so I can just reuse this to hold the sorted data, because as the unsorted part shrinks, the sorted part grows just to match it perfectly. So in the second step, I scan through here for the smallest, I find it, I swap it with the, because when I advance this, this would be the next sorted position. So I swap it with the first unsorted item, and when I'm done, before my current index has gone all the way to the end of the array, just by process of elimination, I know the last thing's in the right spot. So that's the insertion sort algorithm, kind of done in place. How would we write this down using a top-down design approach? Let's do it. So maybe at the very top, you imagine that there's some algorithm that does this, read an array of data, or a list, read a list of numbers. Step 1. Step 2, sort them. And let me put of n numbers so that we know n is the number of items, right? And store in list. So list would be the array. So here's kind of the very top, the top level. This could be abstract, but in fact we know how to do this because we've done it before. So we know how to do it. That process of reading a list of n numbers. Sort them is abstract. This is abstract. We don't know how to do this yet because we're developing that algorithm. And 3 would be, I guess, maybe print the sorted array, right? And I'm not going to develop this. I'm going to assume that we know how to do this. This would just be a count-controlled loop that printed each item in the array. This would be a count-controlled loop that first read the number n, maybe, and then read a list of n numbers from the input. So the big problem here is how we sort them. And to sort them, we're going to look at a selection sort algorithm. So selection sort. I'll just underline that here to say that we are looking at, one of the possible ways that we can accomplish this task. It's not unique. Right? So here's how we do it. We set a variable to represent the first unsorted item. I'm going to call this variable, because it's kind of annoying to write that much, I'm just going to call it first. And I'm going to set it initially, remember I put my pen all the way to the left, that means nothing has been sorted yet, so the first unsorted item lives at index 0. And so while, I'm going to have this while loop that pushes this to the end of the list. It just keeps advancing this, right, until everything is sorted. So I'm just going to write here not sorted, and I'm putting this in red because we don't know how to check that yet. So that would be an abstract step. The next thing that we want to do in selection sort is going to be find the smallest unsorted item. Wow, that's a long procedure name, right? And then next thing that we're going to do is swap smallest with first. That'll be the first unsorted, right? So those are two things that we haven't yet done in this class, so they're red because they're abstract in the sense that I've given them a name, but I haven't told you how to do them yet. And here we're going to set the first unsorted to first minus 1 because this is a count. So we're going to set, I should have made that uppercase to be consistent, first to be first plus 1. And that moves us forward through the array. Okay. So we can begin to look at some of these abstract things like how do we determine whether or not it's been sorted yet. Right? So this is an abstract one. So let's see how we would accomplish that. Why do I have round pens? So not sorted. Not sorted yet. If we fill that in, we know that we're not sorted yet if that first unsorted item, coming back to here, if the first unsorted item is the last item in your array, then you know that everything's sorted. Remember, we didn't have to do anything to search here. So once the first unsorted item is the last item in the array, it's trivially already sorted. Right? Does that make sense? There's only one thing that could be there, and that's the highest element. So when I'm before that, then I haven't been sorted. So I'm not sorted as long as the first unsorted item is less than not n, but n minus 1. Right? So this would be just if the first unsorted is less than n minus 1. So that's how I check that condition, if the first unsorted is less than n minus 1. So we know how to do that. This is no longer abstract. Right? So let's look at the other one. How do we find the smallest unsorted item? And how do we swap the smallest item with the first? I tend to try to want to tackle these not in the order that they're listed, but in the order of what is easier to solve and what's harder to solve, right? And this is probably easier to solve, this one. So how do we swap? I'm just going to write swap out of laziness. And we know that we're trying to swap first with the smallest. And this would be the index of the smallest, and this would be the index of the first unsorted item, right? So we want to swap two things at those indexes. And the problem is, if you imagine that you've got an array of values, and let me just use a post-it note real quick so I can kind of do this, right? So the problem is, if I do a situation like this. Oh, my computer's going to sleep. Okay, so imagine I get a situation like this, and this would be the index of first, so maybe first is, I don't know, 3, right? And maybe this would be the index of smallest. Maybe that's an index, who knows, 5. Not that the index actually matters. And I want to swap them, right? So let's imagine that this is some value x and this is some value y. If I set list first to be equal to list small, then the array looks like this. And I don't have this value anymore. It's completely gone. It's been lost. So before I do that, I need to save this value somewhere. So the way that we're going to do this swap is we're going to set a temporary variable to be the value stored in the list at the position, let's say at the position first. And now I can set the item stored at list first to be equal to the item stored at list smallest. And once that's done, I can set the item stored at list smallest to be the thing that used to be in list first, but it's not there anymore. Now it's stored in temp. So in order to do this, I just needed to use a little bit of auxiliary data, and that's how you swap values. I have no idea whether this is recording, and I may need to edit this out, so I'm just going to say pause. So now we know how to swap. Now we just need to figure out this thing. How do we find the smallest unsorted item? And that's going to be a little bit more complicated, so I'm going to flip the page here. So how do we find the smallest, right? So find the smallest. So what I'm going to imagine is at this point we have an array, and some portion of it over here is in their proper positions, right? So I don't need to worry about those. And here, at this index, whatever this index is, this is first, whatever index that happens to be, that is the first unsorted item. All the way up to position n-1. Okay. And what I want to do is I want to figure out somewhere in here where's the smallest. So what I'm going to do is I'm going to start smallest out being the first item. And then what I'm going to do is I'm going to do a count control loop that starts here and moves to the end of the array. It doesn't need to check here because if that was the smallest, then that's the initial value of smallest, right? But as it goes through here at any point, if this guy is less than that guy, I update smallest to point there. So here's how this would go. So I'm going to set smallest to be equal to the first. Now I'm going to scan through. I'm going to set, I'm sorry, not first, but first. Yeah, I'm going to set small speed at first. I'm going to set something like index or current to be equal to first plus 1. So I'm going to start looking here with some variable called index, and that's going to scan off to the right. And I'm going to use a count-controlled loop here. So while that index is less than n, right? So I'm going up to the n. Right? What I'm going to do is I'm going to check whether the item at index is less than the item at smallest. So if list index is less than the list smallest, so the smallest thing I know so far, if that's the case, then I need to update smallest. I'm going to set smallest to be index. Okay? And regardless of whether that's the case or not, I always need to keep index moving to the right. So I'm going to set index to be index plus 1. So that's a little bit of pseudocode to find the smallest thing. When I'm done, this variable smallest should be pointing at the smallest item in the unsorted portion. All right, take yourself a minute to convince yourself that's true. Let's put this whole thing together into a single algorithm, and I'll do that. I'll do that right here. So insertion sort or selection sort. Goes like this. You set first to 0, and while you're not sorted, so while first is less than n minus 1, we find the smallest item. So I'm going to set smallest to be first. I'm going to set index to be first plus 1. And I'm going to do my count-controlled loop, which is a pattern we should all be really familiar with. And I'm going to look for the smallest one. I'm going to check whether the current one is smaller than the smallest I've seen so far. And if it is smaller, I'm going to update it. And regardless, I keep moving forward because it's a count-controlled loop. My little reminder of where I am with the nesting, because this is a nested while loop. Right. So when I'm done at this point, I can kind of assert that smallest is the smallest item in the list. So now I need to swap. Right. So I'm going to set temp to be the item at list first. I'm going to set list first to be equal to list smallest. And I'm going to set list smallest equal to temp. And that's all still part of this while loop. I could use comments, but this over here is that abstract step to find the smallest. This over here is swap. And this bit right here is not sorted. So there's our complete algorithm. You can number the lines if you want to. Right. Sometimes that's helpful if you want to refer back to things. We've got, it's not a very long algorithm, but we did the complete top-down design process. And now that we have this, we can use that. If I zoom out a little bit and focus, we can use that as a way to visualize the process on an array of data. So in order to visualize that process, I'm going to start by drawing a grid. So let's imagine that we're going to sort this list of values that I came up with here, 3, 1, 2, 5, 4. So we have 3, 1, 2, 5, and 4 in an array. And I'm just kind of, I'm gonna do a couple of things, right? So I'm going to trace through the execution, and anytime I modify this array, I'm going to kind of write the new values below. Right? So let's take a look at this in our code. Our variables are first, smallest, index, and temp, right? So I've got here, let me put them right here, first, smallest, index, and temp. Now I wouldn't be able to trace through code like this for a bigger array because it gets quite big quite fast, right? But first starts off at 0, right? Meaning nothing is sorted. And first starts off at 0, and then I check if first is less than n minus 1. N is 5. Is first less than 4? So this is 0. This is 4. 3, 2, 1. So yes, 0, first is 0, is less than 4. I'm going to set the smallest to first, so smallest is also pointing here. And I'm going to set index equal to first plus 1, so this would be index. While index is less than n, is index less than 5? Yes, index is 1, so 1 is less than 5. If the list at item index is less than the smallest so far. So the list smallest is 3, so is 1 less than 3? The answer is yes. So what I'm going to do is I'm going to set smallest to be index. So smallest is now pointing at 1. Right? First stays where it was. Right? And then I set index equal to index plus 1, so index is now pointing here. And I go back up to the loop. Is index less than n? Is 2 less than 5? Yes. So I'm going to check if list index is less than list smallest. So list index is 2, and list smallest is 1. That's false. And in fact, I know that's going to be false all the way through here. So when I'm done, I'm going to end up down here with index is going to be equal to 5 when I'm done doing all of that. So I'm just going to skip it. And smallest is going to be 1, and first is going to be pointing here at the item 0, which is a 3. So I'm going to set temp equal to list first. So temp is going to be 3. I'm going to set list first equal to smallest. So this is going to become a 1. I'm going to set list smallest equal to temp. So temp out here was a 3. So list smallest right here becomes equal to that 3. And after doing this first step of insertion sort, I have 1, 3, 2, 5, and 4. And how many comparisons did I have to do? Well, I had to do a comparison here to see if 1 was less than 3. I had to check if 2 was less than 1, if 5 was less than 1, and if 4 was less than 1. So I had to do n minus 1 comparisons. I had to do a comparison for each one of those different values. Okay. So now I'm going to proceed with the next step, because first is now pointing over here, and this bit has already been sorted. Alright, so this bit has already been sorted, and this is the unsorted portion. Alright, so first is now 1, and 1 is less than 5. So I'm going to set the smallest to be equal to the first, and I'm going to set index equal to first plus 1. So index is right here. And while the index is less than n, that's true, if the listed item index is less than the smallest, then I'm going to set the smallest equal to the index. So I'm going to update smallest. And by the way, there was a comparison right here, right? And so I just compared. I compared those two. So now I'm going to set index equal to index plus 1. And I'm going to come back up here. Index is less than n. If list index is less than list smallest, is 5 less than 2? I just compared that. That fails, so I don't do anything, and I increment index. If list index is less than, there we go, if list index is less than list smallest, I'm comparing 4 to 2, and 4 is not less than, so I set index equal to 5, and I'm done. So this time I did 1, 2, 3 different comparisons. And so basically a comparison for each one of those values. And when I'm done, the smallest is at item 2, and the first is at item 3. So I need to swap those two. So what I do is I come down here, I set temp equal to list first, which is a 3 again. I set list first equal to list smallest, so this becomes a 2. And then I set list smallest, which is this guy, equal to whatever's in temp, so that's a 3. So now after this step, I've just finished that main loop again. My array is 1, 2, 3, 5, 4. And you know what I forgot to do? I forgot to set first equal to first plus 1. If you caught that, good for you. Alright? So now first should be pointing here. And I've got the first 2 items sorted. Right. I'm not going to update all those arrows, it gets too cluttered, but right now the first item is 3, the current index is 5, I'm going to compare 5 to 3, and 5 is bigger, so 3 stays the smallest. I'm going to compare 4 to 3, and 4 is bigger, so 3 stays the smallest, and so smallest is 3 and first is 3, so I'm going to swap that with itself. So now first is 4, first is pointing at 5, index is pointing at 4. I'm going to compare 4 to 5, and 4 is smaller, so this is the smallest. And when I'm done, I'm going to swap the 4 and the 5, so 4 and 5. And now first is equal to 4, but 4 is not less than n minus 1, so the whole algorithm is done. This is the last step. And indeed, it's all sorted. Right? So I hope that was not too messy, but we can see that at each step you did n minus 1 comparisons, right? So if I have n numbers, the total number of comparisons is going to be the sum from I equals 1 to n of I minus 1, right? And which is of course equal to the sum n from 1 to n minus 1 of I, and that's an arithmetic series, and those things have the solution. It's going to be n times n minus 1 over 2 different comparisons needed to do selection sort. So if you wanted to keep track of that, it makes sense. It's about n squared over 2 minus, n over 2, right? So it's n times n minus 1 over 2 comparisons to do this selection sort. We don't like to be that precise, but we're going to say it's order n squared comparisons. So this is a slow algorithm to compare a list of numbers, but it gets the job done.